Okay, well, first of all, thank you all for attending, and thanks for the introduction, Feliciano. So after the general overview about EPW and EPWpy by Sabia, the idea of this second lecture is to show you a couple of more specific examples of things that one can compute with EPWpy. And the two examples will be carrier transport and self-tracked Polarons. So the idea for this lecture, I will first introduce the topic, what is carrier transport and what is Polarons in general, why are they important, and then I'll jump into the two topics of the lecture in more detail, namely the Boltzmann theory of carrier transport and the ab initio Polaron equations. And then finally, I will conclude with some general remarks. So as Sabia mentioned in his introduction, probably one of the most tangible manifestations of electron-phonon interactions in our daily lives are that electronic components heat up when they operate, right? So that's something that we all experience with our phones or laptops, but that's also something that big supercomputing centers care a lot about, and that's because they need to spend a lot of effort to try and dissipate that heat from the computers. So this is a picture that I took myself in the last EPW school in Austin. And this is a subsystem of the Frontera supercomputer at TAC that is actually submerged in oil so that it can efficiently dissipate this heat. So I guess probably everybody has an intuitive notion of why this happens, and I'll try to illustrate it here with a cartoon. So one can imagine that as electrons propagate through a material, from time to time they will suffer collisions with, say, defects or with lattice vibrations, right? And in these collisions, they will leave some of their energy into the material. This extra energy needs to dissipate somehow, and that's how heat forms, right? So in essence, it's a manifestation of the interaction between electrons and the phonons in our material. But probably for the purposes of this lecture, the reciprocal effect is more interesting, and it's the effect that in most materials, the resistivity increases as we rise up the temperature. So here, for example, I'm showing as an example anatase titanium dioxide. This is a material that it's used in solar cells, photocatalysts, and in many other applications. And as you can see in the figure on the right here, the resistivity increases as the material heats up. And this can be understood also with the same cartoonish picture. So one can imagine that as the electron is propagating, if the temperature of the material increases, the amplitude of the lattice vibrations also increase, and therefore the probability of scattering, an electron scattering with these lattice vibrations gets higher. And as a result, it's more difficult for this electron to propagate, and the resistivity increases. So this happens in anatase titanium dioxide, and it happens in many semiconductors and in metals. But this situation is not necessarily always the case. So if one goes to more complex materials, here I'm showing as an example this manganite compound, that it has a tilted perovskite lattice, as you can see here. So in this material, in this experiment, what the authors did is to substitute lanthanum with strontium. And with this, what they could do is they could control what was the doping of the material. They were adding holes into the system and making the material more and more metallic. And in the figure on the right here, I'm showing experiments for resistivity as a function of temperature for different levels of doping. So as you can see, for relatively high doping levels, the resistivity follows the expected trend that we discussed in the previous slide and increases with temperature. But however, when the doping is low, if you look at the upper part of this figure, you see that actually the resistivity is decreasing as the temperature goes up. So that means that somehow the carrier transport is more effective as the temperature goes up, right? And that goes against the first intuition we discussed before. But actually, one doesn't need to go to such complex materials. So, for example, in titanium dioxide, using the same exact chemical composition, but a different structural motif in the rutile polymorph, experiments have shown that resistivity in this case also decreases with temperature. So it seems that the mechanism of carrier transport is completely different in rutile as opposed to anatase. So how can we understand all this? So for that, I propose a very simple thought experiment that goes as follows. So imagine we have a semiconductor or an insulator in which all the valence bands are full and all the conduction bands are empty, as I show here on the left. So this cartoon on the right represents the lattice in real space. So dots would be atoms, and the solid black line would be the periodic potential that this lattice generates. So now imagine we add an electron on top of this insulating material while keeping the atoms totally fixed, frozen, right? So since the material keeps the same periodicity as before, this electron will need to occupy the bottom of the conduction band. And as a result, its associated electron density will be totally periodic, right? We'll inherit the periodicity of the lattice. Now imagine we slightly distort our lattice. We move some of the atoms a little bit. And what you will see in this case is that the potential that the lattice is generating will get also a little bit distorted, as is shown here with the dashed lines. And what it might happen is that if the electron-phonon interaction is weak, this change in potential will be small. And as a result, the electronic state will stay as it was before, will be totally periodic, and it will stay at the conduction band bottom. And this distortion of the lattice will act just as a scattering center, and thus it will limit the conventional transport that I showed in the first slide. However, if the electron-phonon interaction is strong enough, what it might happen is that this change of the potential is deep enough that creates a potential well in which bound states can emerge. So for these bound states, since the periodicity is broken, they get localized around this potential well. And since the periodicity is broken, as I was saying, they cannot lie in the bottom of the conduction band. And in the energy wave vector picture, they appear as a localized gap state in our band structure, right? So this will be the strong coupling limit. Now, when these localized charges move, now you have to imagine that they need to drag around the lattice distortion associated with them, right? So that's what I'm trying to illustrate here in this cartoon. So what happens in this case is that for this localized charge to hop from one lattice side to the one next to it, it will need to drag around this lattice distortion, and as a result, it will need to overcome an energy barrier, as shown here schematically, right? So now what happens is that as temperature goes up, there is a higher probability that this electron falls into this transition state, and as a result, it's more likely that this polaron ends up hopping to the nearest neighbor site. And that's why when we increase temperature in this strong coupling regime, the transport is more effective and the resistivity goes down. So this is the notion of self-trapping and why it is different from conventional band transport. So after this general introduction, now I'll go into a little bit more detail of how we can compute both of these regimes with EPW. I will show the general theory. I will show also the equations that one needs to solve. And then finally, I will show how one can streamline all these calculations with EPWpy. So let's first focus on the Boltzmann theory of conventional, let's say, diffusive transport. So in this theory and in the EPW calculations that you will perform in the hands-on session, the central quantity that you will like to compute is the carrier mobility. So let me first introduce the notion of what that means for you to get an intuitive picture. So let's go back to this cartoon of propagating electron on a lattice. But let's first imagine that we do not apply an electric field. As I was saying, this electron will suffer from collisions with defects, with lattice vibrations, and so on. And as a result, it will change its trajectory. And on average, it will follow some kind of a Brownian motion, and it will not displaced, right? So one can compute the mean velocity of this electron, and it will be 0 on average. If one applies a finite electric field, however, what will happen is that this electron will get accelerated in between collisions, and as a result, this trajectory will be elongated along the direction of this electric field, and as a result, it will move, right? And it will have an average velocity that is called the drift velocity. So in this context, the carrier mobility is defined just as the proportionality ratio between the external electric field that we apply and the average drift velocity of the electrons. So this is the carrier mobility. Now, how can we compute this carrier mobility from first principles? So ideally, what one would like to do is to treat the problem fully quantum mechanically and to analyze each of the electron individually and see how its wave functions propagates in time and so on. But in practice, it's much more convenient to turn into a statistical study and focus on the probability distribution function of the electrons. So once, let's say, the main idea of this strategy is to ask the question of how many electrons do we have in a particular region of phase space. For example, here I'm showing the phase space momentum and real space. And we will ask how many electrons do we have in this gray box here. And then we ask the question of how do these probability distribution function evolve with time, right? So the answer to this question mathematically lies in the well-known Boltzmann transport equation that I'm showing here on the top right of the slides. So in this equation, one has the drift terms on the left and the collision terms on the right. One has the evolution of this probability distribution function, one has the diffusive term, and one has the force term. In our case, since we are dealing with electrons in external magnetic fields, the force will be given just by the conventional Coulomb and Lorentz force that I showed here. And for simplicity, we will only focus on steady state transport. So what happens once everything has gone to equilibrium under this external field. And we will also focus only on homogeneous materials. So we will neglect the spatial dependence of this probability distribution function. So after doing that, we see that the Boltzmann transport equation gets simplified to this equation I give in the bottom right of the slide. So we will go back to this equation later. But first, let me show you now how can one translate this notion of probability distribution function and Boltzmann transport to the case of solid state physics and electron bands. So in a solid material, as you know, the electron states can only occupy certain discrete levels that are typically shown in this type of energy wave vector diagrams, which are called the band structure diagrams, right? So one can show that in a semi-classical picture, these electron states form wave packets whose proof velocity will be given just by the slope of this band at a particular wave vector. And this is what we call our electron velocity V. Now, the probability distribution function in this case will be just the probability of having one of these electron states occupied, and it will be given by this occupation factor F, that in absence of an external electric field will be given by the Fermi-Dirac distribution function, right? So in this context, one can define the current density as just the summation of the contributions of each occupied electron to the current. So we will need to sum the velocity of each occupied electron and then divide by some factors to get the proper units of the current density. Now, in the absence of electric field, this occupation factor will be totally symmetric, right? And as a result, one can show that this summation, this integral will always vanish, right? And we will not have net current in the absence of external electric field, as one would expect. However, once we apply an electric field, what happens is that our electron states get their momentum changed, right? This distribution function shifts a little bit to one side. The symmetry is broken, and one can find a finite contribution to the total current density. Now, how does all this relate to the mobility? Well, one can more formally define the mobility in line with what I showed previously as the derivative of the current density with respect to the external electric field with some prefactor. And now, if we assume that we are dealing with small electric fields, and that's basically typically the most relevant regime for electronic operations, one can expand in a Taylor expansion this occupation function to linear order, and then substitute this expression on the definition, and one finds that the mobility is given by the weighted average of the velocity of our electron states, in which the weights are given by the variation of the occupation function with respect to the external electric field, right? Okay, so this is the point now when I connect back to the Boltzmann transport equation. And what I'll do first is go back to this expression and now explicitly write down the collision terms, focusing only on electron-phonon interactions, right? So one thing to notice is that there might be several scattering events that might affect the evolution of this F. There are scattering events that bring electronic states from anywhere else to our NK states, let's say, and there are collision events that take out our occupied state in NK to any other place. And in all these scattering events, the energy has to be conserved, and these are given by these delta functions. And it might happen due to both phonon emission or phonon absorption. And the occupation of these phonon states are controlled by this Bose-Einstein occupation function. Now, if we take this expression and we take the derivative with respect to electric field on both sides, the equation to which we arrive is this one. And here I've done a little bit of ordering of the terms just to make it more clear. So the two main messages here are that this expression might look a little bit involved, but all of the ingredients, if you look at it in more detail, are things that we can compute with DFT, DFPT, and EPW, as Sabia was mentioning before. So here we have the electron eigenvalues, we have the phonon frequencies, and we have the electron-phonon matrix elements. And the second thing to note is that this equation has to be solved self-consistently because we have the variation of the occupation factor on the left-hand side and also on the right-hand side of the equation. So one thing that people have done in the past to make this equation more simple is to neglect completely this second term and to focus only on the first line. And this is typically called the relaxation time approximation to the Boltzmann equation, while the full solution of the Boltzmann equation is typically called the iterative Boltzmann transport equation. So one can solve this equation with either the RTA or the full one. And after replacing the solution of this equation in the expression I gave you before, one can compute the mobility in practice. So this is how you will compute the mobility later in the hands-on session. One thing to note is that I've condensed some of the things in this quantity with tau, represented with tau, and this is the carrier lifetime. Its explicit expression is this one. Again, the ingredients are the same as I mentioned before. But what I wanted you to note here is that the delta functions associated with energy conservation limit the scattering events to a region of the Brillouin zone that it's very localized around the Fermi energy of our system, and it is within the range of the phonon frequencies. And as a result, we need very dense grids, and that's why EPW, one-air interpolation, and EPWpy will be very useful to solve this type of equations. Okay, so the workflow is very similar to the one Sabia mentioned us in the general introduction. So we will first start from our crystal structure. You can obtain that from Materials Project, the pseudo potential from pseudo dojo, and so on. And the first step will be to perform a self-consistent field calculation, for example, with quantum espresso, and then a phonon calculation in a coarse grid and a non-self-consistent calculation in a coarse grid. After we obtain that, we will calculate the electron-phonon matrix elements in the Vanier representation using Vanier 90 and EPW codes, and then we will interpolate these matrix elements and all the quantities to a fine mesh with EPW. And this stage, one typically wants to make sure that the interpolation is good enough. So typically one wants to test what happens if I change the coarse grid here, how that affects my interpolation to make sure that everything is converged in that respect. And after obtaining convergence with respect to the coarse grid, one also needs to converge with respect to the fine grid due to the reasons I outlined in the previous slide. And after making sure that everything is converged, one can compute the mobility and analyze its dependence with temperature and so on. So as you can see, there's multiple steps in the calculation, multiple codes, and basically there's many places where a calculation can go wrong. And that's why EPWpy can be useful, because it can streamline all these calculations and make them more automatic. Okay, so just before ending with the first part of the talk, I wanted to give you a couple of examples. So this is an example on silicon, calculations done with EPWpy by Samuel Ponce and collaborators. So this material is typically taken as a benchmark. And here what I'm showing is with squares and circles, I'm showing experimental data for electron mobility as a function of temperature. And the solid red line represents ab initio calculations done with EPW. And as you can see, the agreement is very, very good with respect to experiment. And note that this is not a fitting to the experimental data. So it's really an ab initio calculation without external parameters. So this is to show that the agreement is remarkable, at least in this case. But if one performs more systematic benchmark across different semiconductors, for example, as it was done here in this subsequent work by Samuel Ponce and collaborators, what you find is that these methodologies typically get mobilities in very good agreement with the experiment. So here, excellent agreement would be the diagonal line. And as you can see, the error on average is in around 30 or 40% when one solves the Boltzmann transport equation. So the main take-home message at this point is that these calculations and other calculations by other groups, independent implementations and so on, are showing that at this point, we are reaching a level of maturity where one can perform really predictive calculations of, let's say, standard band-like transporting materials, and this enables the ab initio design and discovery of new materials for electronic applications. So with this, I finish the first half of my talk, and I jump into the second part, which is on the ab initio Polaron equations. So let's go for a moment back to Polaron self-trapping. So as I mentioned, the Polaron is nothing but a composite quasi-particle formed by a localized charge and its associated lattice distortion. Now, this concept of self-trapping that I introduced in the introduction, it was already outlined by Landau and Pekar almost a century ago. And since then, it has motivated a lot of theoretical work by many, many people around the years. But I wanted to highlight that during the past 10 years, more or less, there's been an upsurge of development in the ab initio community to try and model these objects from first principles. You can find some references here. These are not exhaustive, but you can find more references and a more detailed discussion in this review by Cesare Franchini and collaborators. And I think that the main reason why there's been this renewed interest in these objects is that there's been also a lot of developments in the experimental side that can measure the microscopic nature of polarons in real materials now. So here I'm showing just some examples. We have discussed already the transport measurements, but polarons also leave a mark in optical properties of materials. So for example, in some materials, there's a very big shift in between the absorption peak and the emission peak. Here I'm showing as an example of double halide perovskites. And in this material, people ascribe this big shift to the localization of excitons or the formation of self-trapped excitons. But probably more interesting in our discussion are the two experiments on the bottom, because these access the microscopic nature of polarons. The one on the bottom left are ultra-fast pump probe X-ray diffraction experiments on lead halide perovskites. And here what the authors could measure was the formation of large polarons in this material and could track their formation in real time. So they could analyze what happens as polarons gets localized in real time. And the one on the bottom right, it's more recent, and it's an AFN experiment in which the authors could create and manipulate single polarons on the surface of an oxide using the tip of an AFM. So this is giving very promising prospects toward control and manipulation of single polarons. So how do we model polarons from first principles? So the concept is relatively simple in the context of DFT calculations. So what many people have done in the past 10, 15 years is to do what is called direct supercell calculations of polarons. So in this case, the first step is to first build a supercell of your crystal, and then one adds one electron, just as in the thought experiment we did in the introduction. So after adding this electron, one now breaks a little bit the symmetry and lets the system relax. And what might happen is that in the end of this relaxation, one finds a state in which the extra electron is localized and the atomic lattice is distorted. And if the energy of this distorted configuration is smaller than the periodic configuration, one can conclude that the polarons are stable in this material. So these are very useful calculations to model polarons, but they suffer from two main challenges. The first one is that this type of calculations depend a lot on the exchange and correlation functional that one uses in the calculation. And this is due to the well-known self-interaction problem in DFT calculations. And the second one is more practical, and is that one can only model polarons as large as the supercell size one can afford in these direct DFT calculations. So let us look into more detail on the two of these problems and how can we solve them. So to begin with, here I'm only writing the total energy in density functional theory. It's nothing special. We have the kinetic energy, Hartree energy, exchange correlation, and then we have Coulomb energy between the ions and the electrons, and the Coulomb repulsion between the ions. So this will be the energy for a, say, semiconducting or insulating crystal. And we want to ask the question of what happens when we add one extra electron to the system. So in this case, the total energy of this n+1 electron material can be written as follows, where I have highlighted the extra terms in blue and red. So the terms in blue represent, this psi represents the wave function of the extra electron that we add, and the U in red represents the displacements of the atoms with respect to the periodic configuration. So here we can identify several things. So for example, one can see that in the Hartree term, there will be a spurious interaction between the Polaron wave function with itself, and something similar happens in the exchange and correlation. And as a result, one can identify explicitly what are the self-interaction terms, and one can remove them, let's say, analytically. And the second thing we want to do to move towards practical calculations is to expand these displacements to lowest order within the harmonic approximation. So after taking into account these steps, and after several other relatively straightforward algebra steps, one finds that the formation energy of the polaron, that is defined as the energy difference of the distorted configuration with respect to the periodic configuration, can be written as a functional of the polaron wave function psi and the displacements u only. So it will be a functional of these two functions. And as a result, if we want to minimize this functional, we can do so using Lagrange multipliers. And after performing this variational minimization, one falls into a set of coupled equations for this psi and this u that will need to be solved self-consistently. Right? So with this first step, what we have done is to solve the first problem of the self-interaction, because there is no self-interaction in this equation by construction. But we are still we have still the challenge of the supercell size, right? Because these expressions are still written in real space, and these integrals, for example, will need to be taken on the full Born-Kalmar supercell. So in order to go around this, in EPW, what we do is we expand the Polaron wave function in terms of periodic Bloch waves that are given by the Concham states, for example, and we expand the displacements in terms of the phonon eigenmodes. So what this enables is to rewrite this coupled set of equations in reciprocal space. And so the interesting bit about this expression now in the bottom is that the ingredients one need to solve these equations are the Concham eigenvalues, the phonon frequencies, and the electron phonon matrix elements. So again, these three quantities are objects that one can compute very efficiently in EPW, right? So that's why these expressions will be very useful for us. And these are typically called the ab initio Polaron equations. Okay, so just to show you one example of how real space, reciprocal space connection works, I'm showing an example of electron polarons in lithium fluoride. So on the left-hand side, I'm focusing on the electron part, and on the right-hand side on the distortions. You can see that in this case, the electron polaron wave function is very large in real space, And as a result, its Fourier components in reciprocal space will be localized around the conduction band bottom. And similarly for the displacement. So you can see that displacements are also very delocalized in real space. And as a result, the coefficients in the phonon eigenvectors are also localized around the gamma point. And one can also identify which are the relevant phonons triggering this Polaron formation. And in this particular case, one sees that it's mainly governed by the LO phonon modes near to gamma. And as a result, one can identify these large Polarons as Frolic Polarons. So maybe one thing that I wanted to highlight in this slide is that this real space figure corresponds to a 10 by 10 by 10 supercell. And if one does the math, that corresponds to a supercell of around 300 atoms. So 3,000 atoms, sorry. So this is something that certainly one cannot do via a direct supercell approach. So this type of large Polarons can be modeled using the reciprocal space formulations. That's its real power. Okay, one last mention in the theories part is that one can also introduce these expansions into the formation energy expression, and one can write the formation energy as a function of these A and K and BQ nu coefficients only. And for example, if one computes the formation energy for electron Polarons in lithium fluoride, one sees that it's relatively small, and that's to be expected because the localization is not strong. But if one repeats the calculation for holes, in this case, one sees that the Polaron is very, very localized in real space, and as a result, its formation energy is very large, right? So it's very stable, are very stable Polarons. Okay, so now let's move to practical calculations. Let me show you first what is the typical workflow one needs to solve. So typically one starts the calculation with an initial guess of the coefficients A and K. And from here, one computes the BQ nu coefficients using one of the equations I showed you before. If one integrates these BQ nu coefficients into the equation of the electron part, one can define an effective Hamiltonian for the Polaron that then can be diagonalized to obtain the A and K coefficients and the Polaron eigenvalue. And at this point, one can compare the A and K coefficients that we obtain with the initial A and K coefficients that we set as initial guess. And if they look very different, we go back to this step of the loop and we repeat until set consistency is achieved. And after this is done, we can move on to plot the wave functions, the displacements, and the formation energy and post-process solar calculation. So one particular thing I wanted to maybe spend a couple of minutes on is the periodicity. And for this, I'm focusing on a two-dimensional system just for simplicity on a square lattice. Left-hand side shows the Brillouin zone and right-hand side shows the real space lattice with the direct vectors shown as blue arrows. So for example, if one solves the Polaron equations in a 2x2 grid on reciprocal space, that corresponds to Polarons in a 2x2 supercell in real space, because we are always using von Karman periodic boundary conditions. And as a result, the Polaron wave function will have repeated images in this 2x2 supercell. If we increase the momentum space grid in which we are solving the equations, for example, to a 4x4 in this example, then we're moving into a 4x4 supercell in real space. And as a result, the periodic images now are separated by 4 unit cells. So we can conclude 3 things from this. The first one is that since these periodic images interact with each other, the energy that we obtain from our calculation will depend on the reciprocal space grid that we're using. That's the first. The second one is that as a result, if one wants to obtain what is the energy of an isolated Polaron in the middle of the material, one would need to extrapolate our results to infinite supercell size or infinitely dense reciprocal space grid. And the third one is that if the grid that you are using is not dense enough, these periodic images will start to overlap and they will form bonding and antibonding orbitals. And as a result, we will not find any localized solution. So this is illustrated here for lithium fluoride. Here I'm showing the formation energy of the Polaron as a function of the supercell size, which is controlled by the grid in reciprocal space. So you can see that the energy depends on the grid, and to obtain the formation energy, we need to extrapolate to the infinite grid limit. And you can also see that for very small grids, that is for very small supercells, the Polarons start to overlap, and we don't find any localized solution until we reach the point in which these Polarons start to get isolated, and we get a transition to the isolated and localized Polaron scenario. And we call this a Polaronic metal to insulator transition. Okay, now for post-processing, I wanted to mention two things that typically one always wants to explore after performing these calculations. The first one are the atomic displacements. So these are relatively easy. One just use the expansion that I showed before between the displacements in real space and phonons in reciprocal space. So plugging here the BQ new coefficients one obtains from the calculation, one can transform and plot the displacements in real space. And actually, this is very useful for us because it's a real quantity and it's very useful to compare and to set the threshold for the convergence. And this is what is actually done in the calculation. So convergence is set, when the difference between the maximum displacements between one iteration and the previous one is lower than a certain threshold. Now, for the Polarons wave function, one can also use the expansion in reciprocal space and represent it as a linear combination of block wave functions. But it turns out that it's much more convenient to use the Bannier expansion of the Polarons wave function. That means representing the Polarons wave function as a linear combination of Bannier functions that are shown here by the W. And these are the same Bannier functions that Xavier was mentioning before. And for that, one only needs to transform the A and K coefficients that we obtain in EPW to the Bannier coefficients. And from there, one can obtain the Polarons wave function. Now, how can we now analyze what are the most important phonons or the most important bands taking place into these Polarons? So we can do an interpolation the same way that we do interpolation of band structures using EPW. So we start with the coefficients in reciprocal space one obtains from the ab initio Polarons equations, then transform to real space, to the displacements and to these AR coefficients. And one can perform then an interpolation onto an arbitrary path in reciprocal space to analyze what is the shape of these coefficients along a particular asymmetry points in reciprocal space. Okay, so now for the workflow, in this case, it will be very, very similar to the transport. So we will need to perform all the preliminary steps as before. Now the difference is that this change of K grid in the fine mesh is not a convergence parameter anymore, because we are actually dealing with Polarons in different sizes, so different supercells. So what we will need to do is to repeat this calculation for an increasingly dense grid and then extrapolate to infinity. So after we do that, we can then analyze our Polaron and do post-processing, see the wave functions, and so on. And again, all this is something that can be streamlined very efficiently with EPWpy. This is just to connect again with the introduction. So this method has been now used in a handful of materials, and we have obtained results in different materials for different types of Polarons, large and small. And here I'm just illustrating this going back to titanium dioxide and showing that Chen Van Dai in his work, he recovered what was expected from experiments that when applying EPW Polaron calculations to rutile titanium dioxide, one obtains very small Polarons localized in a couple of unit cells, while performing these same calculations in anatase, one obtains a very, very large Polaron that is very delocalized in real space, as expected from the band-like transport experiments. Okay, if I have a couple of minutes, I will just mention briefly how to compute the Polaron energy landscape, just to connect with the transport and the energy barriers we mentioned in the introduction. So I cannot go through the math here, but one can show that if one takes the formation energy expression that we had in real space and minimize only with respect to the wave function, one can leave the displacements as a free parameter and obtain what would be the formation energy. So what is the energy of the n+1 electron system at any given atomic configuration? And then if one transforms this atomic configuration to reciprocal space, one can plug in this BQ new coefficient and obtain the formation energy for any distortions that we want. And in particular, if we perform a configuration coordinate diagram going from the distortion corresponding to the Polaron sitting in one side and then jumping into the next one, we can compute this formation energy in various steps along this path, and we can extract what is the energy barrier that the Polaron will need to overcome in order to do hopping-like transport. So the workflow is somewhat similar. One starts with a displacement configuration that now is not minimized, is taken as an input. and then builds the effective Hamiltonian as before and diagonalizes it. And from here, the difference is that one doesn't need to perform self-consistent calculations anymore, because remember that we are not minimizing with respect to the displacements. We only take the eigenvalue, and from here and the Bicu-Nu coefficients, we obtain what is the formation energy for this specific atomic configuration. And then we can repeat these calculations for several points along the configuration coordinate, and we can obtain the energy barrier. So just to show one example, these are calculations that we did for this double halide perovskite. In this material, the electron polaron localizes very strongly in one octahedra, and we performed the calculation for what is the energy barrier to jump from one octahedra to the one next to it. And we saw that the energy barrier was pretty large, and that's explained the low mobilities observed in this specific material. But maybe more interestingly, we also explored the energy landscape of the Polarons more briefly, or more broadly, sorry. And we found that in this material, actually, there's more than one Polaron that one can find. There are multiple solutions. And with this type of calculation, we can explore what are the energy barriers to go from one solution to the other, or to go from the periodic configuration to either of the solutions. And we found that, for example, in this material, there is no barrier to go from the periodic configuration to the large Polaron, but that there is a barrier to go from the large Polaron to the small one. So one would expect that as one dopes the system first, the electron occupies this large Polaron state, and then after only some time, it will jump into the small Polaron and more stable solution. And this went very much in line with experiments in this material where they observed a two-time localization. So at short times, they observed mobility that decreased with temperature, as expected from large Polarons or conventional bands, while at longer times, they observed mobilities that increased with temperature, showing temperature-activated hopping Polaron hopping transport in line with our results of more stable small Polarons in these materials. So with this, I will conclude. Just to summarize, I wanted to highlight that both transport and Polaron calculations require many calculation steps, are quite involved, but that EPWpy can streamline all this process and make it more automatic and robust. And then I also wanted to highlight that while Boltzmann transport equations for band-like transport are very mature and allow for predictive calculations, it is my opinion that for Polarons, we are making very important steps towards making predictive calculations of Polaron hopping activated transport, but we are not yet. We are still at the level of formation energies, wave functions, integral space, and so on, and that more work is needed to get to the same level of precision as we have in Boltzmann like transport. So with this, I finish, and I thank you all for